Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is motor drives. Our objective is to introduce a power electronics device known as a motor drive that varies the magnitude and frequency of applied voltage to vary the resultant torque and speed of a motor under its direction. We'll summarize the internal operation of a motor drive and examine specifications, features, and basic parameters of motor drives. This lecture operates under the assumption you are familiar with the operating principle of three-phase AC motors. For those necessitating a review of this topic, you are encouraged to revisit the Rotating Magnetic Field lecture available at the Big Bad Tech channel. Additionally, it is presumed the viewer has a general understanding of AC circuit analysis. It should be noted that this introductory lecture does not dive into manufacturer idiosyncrasies or operation procedures for specific motor drives and will largely summarize the inner workings of motor drives. Later lectures will examine applications of specific motor drives, as well as discuss in detail those power electronics devices internal to a motor drive that make this possible. Expectations having been properly directed, let us continue. As you are no doubt aware, the synchronous speed, the speed of the rotating magnetic field produced by the stator of a three-phase AC motor, is a function of the number of pole pairs per phase and excitation frequency of the applied voltage. The formula I use to determine the synchronous speed is 60 times the applied frequency divided by the number of pole pairs per phase. Specifically note the term I'm using in this formula, pole pairs per phase. This means a three-phase AC motor with 12 poles has 4 poles per phase and 2 pole pairs per phase. Using this formula, it should be readily apparent that when the number of pole pairs per phase is held constant, synchronous speed is directly proportional to frequency. As frequency increases, synchronous speed increases. Conversely, as frequency decreases, synchronous speed decreases. As an example of frequency's direct influence on synchronous speed, consider a three-phase AC motor with 2 pole pairs per phase operated at 50 Hz. This motor would experience a synchronous speed of 1500 RPM. If excitation frequency increased to 60 Hz, the synchronous speed would proportionally increase to 1800 RPM. Similarly, it should be well within your capacity to understand that when excitation frequency is held constant, synchronous speed is inversely proportional to the number of pole pairs per phase. As the number of pole pairs per phase increases, synchronous speed decreases. Conversely, as the number of pole pairs per phase decreases, synchronous speed increases. As an example of the number of pole pairs per phase inverse influence on synchronous speed, consider a three-phase AC motor with 2 pole pairs per phase operated at 60 Hz. As previously, this motor would experience a synchronous speed of 1800 RPM. If excitation frequency remained at 60 Hz, however, if the motor employed 3 pole pairs per phase, the motor would experience a slower synchronous speed of 1200 RPM. Given most distribution systems operate at fixed frequency, 60 Hz being the US standard and 50 Hz being the EU standard, this leads to quantum levels of synchronous speed. In the US, it is common to experience motors with a synchronous speed of 3600, 1800, 1200, 900, 720 RPM, and so on. All these speeds being a result of the number of pole pairs per phase since frequency is fixed. In the EU, one would typically experience motors running at 3000, 1500, 1000, 750, 600 RPM, and so on. It should be noted that increasing the number of pole pairs per phase increases the physical size of a similarly rated motor. For example, a 1.5 kilowatt motor with 4 pole pairs per phase might be twice as big and heavy as a 1.5 kilowatt motor with only 2 pole pairs per phase. To briefly examine this tangentially related topic, given mechanical power is the product of the twisting force known as torque and rotational speed divided by 9.55, it can be shown that the similarly rated larger motor turns slower but exerts more torque because of the increased number of pole pairs per phase. Assuming the motors are operated at 60 Hz, the one with 2 pole pairs per phase rotates at 1800 RPM, and the one with 4 pole pairs per phase rotates at 900 RPM. Rearranging the mechanical power formula suggests torque equals 9.55 times mechanical power divided by rotational speed. Substituting in the given values, we find the one with 2 pole pairs per phase exerts roughly 8 Newton meters of torque, and the one with 4 pole pairs per phase exerts roughly 16 Newton meters of torque. For those wishing to review mechanical power as it relates to electric motors, I direct your attention to the Mechanical Power, Torque and Rotational Speed lecture available at the Big Bad Tech channel. Returning to the topic at hand, note the synchronous speed is the speed of the rotating magnetic field produced by the stator and not the actual speed of the rotor. This may take some explanation. Two notable classes of three-phase AC motors exist: synchronous and induction machines. The rotor of a three-phase AC synchronous motor, as the name implies, is synchronized with that of the rotating magnetic field produced by the stator when inside its operational range. The rotor speed of a synchronous motor is therefore equal to the synchronous speed inside its operational range. Synchronous motors can be of the permanent magnet or electrically excited variety. The rotor of a three-phase AC induction motor, in contrast, must necessarily lag behind the rotating magnetic field produced by the stator for the induction process to work at all. The rotor speed of an induction motor therefore has a more complex relationship with synchronous speed that must take into account applied load. The speed-torque curve of a generic induction motor shows that even at no load conditions, the rotor speed is slightly less than the synchronous speed, and when operated at rated load conditions, even less. Though the full range of an induction motor includes all possibilities of rotational speed down to 0 RPM, they customarily only operated inside a small window where speed and torque play nice and linear. Induction motors can be of the squirrel cage or wound rotor variety. Long story short, while synchronous speed remains quantized at specific levels, notably 3600, 1800, 1200 RPM, and so on, actual rotor speed for induction motors range around these fixed values. Consider a three-phase AC squirrel cage induction motor with 2 pole pairs per phase operated at 60 Hz. The synchronous speed might be 1800 RPM, but even in no load conditions, the rotor might rotate at only 1790 RPM. When experiencing rated load, the rotor speed might drop to 1670 RPM. When exerting maximum torque, the rotor speed may drop all the way to 1100 RPM. However, if it remained here for any length of time, the motor would quickly enter overload conditions. Assuming we operate the induction motor using a fixed excitation frequency within its intended range, this still results in specific quantized levels of speed. The only wiggle room with respect to speed you've really got is the choice of motors, which, if you think about it, does provide a primitive means of speed control. Assuming 60 Hz, if an application necessitated a nominal speed of 3600 RPM, one chooses a motor with 1 pole pair per phase. If, however, the application necessitates a nominal input of 1800 RPM, one chooses a motor with 2 pole pairs per phase, and so on. For applications necessitating 2 distinct speeds, a clunky old-school method of speed control made use of separate winding motors. Separate winding motors basically consisted of stators with several pole pairs per phase that could be connected or disconnected as needed to change the resultant synchronous speed given a fixed excitation frequency. When the motor needed to run at high speed, the separate winding motor was connected such that it ran using less pole pairs per phase, such that synchronous speed was higher. When the motor needed to run at low speed, the separate winding motor was connected such that it ran using more pole pairs per phase, such that synchronous speed was lower. This made separate winding motors more expensive, mechanically complex, and a little bit larger than necessary, but did result in 2 distinct speed ranges, although still exhibiting a large no man's land between the 2 ranges. The obvious problems are those scenarios necessitating a nominal input speed of something other than the readily available 3600, 1800, 1200 RPM, and so on. A convenient solution to these scenarios are mechanical step-up or step-down gearboxes or belt and pulley combinations with a gear or pulley ratio such that input and output rotational speed are appropriately exchanged for torque. For example, consider an application necessitating a nominal input of 2000 RPM, a rotational speed figure ordinarily stranded in the large no man's land between single pole pair per phase and 2 pole pair per phase 3-phase AC induction motors. Assuming 60 Hz, one could purchase a 3-phase AC motor with a single pole pair per phase with a synchronous speed of 3600 RPM and a 1.8 to 1 step-down gearbox to arrive at the nominal 2000 RPM output. Similarly, one could purchase a 3-phase AC induction motor with 2 pole pairs per phase with a synchronous speed of 1800 RPM and a 1 to 1.11 step-up gearbox to arrive at the nominal 2000 RPM. Either combination results in the desired nominal rotational speed of 2000 RPM. It should be noted that most fixed-speed machines making use of gearboxes actually step motor speed down more than these simple examples suggest. Additionally, it should be noted that the gearbox exchanges speed for torque. As speed goes down, torque goes up, and vice versa. Regardless, given the right ratios, through mechanical modification of pre-existing speed levels, we've now effectively thrown wide open the doors to a theoretically infinite range of speeds. This being said, given a fixed excitation frequency, a fixed number of pole pairs per phase, and a fixed gear ratio, output speed is still fixed. While suitable for some applications, this isn't always the best means of control for others. Consider a pumping or air handling application in which infinitely variable flow rates are required. Given flow rate, a measure of volume per unit time, is a product of volumetric displacement per revolution times revolution per unit time. A pump with a fixed displacement value, operated at a fixed speed, will always produce a constant flow rate. Long story short, flow rate is a direct reflection of rotational speed. A separate winding motor might be able to produce 2 distinct flow rates. However, what we really want is infinitely precise tuning depending upon conditions. Old school flow control methods for hopelessly outdated systems, believe it or not, ran a motor at full speed all the time and simply tightened down a damper or diverted flow elsewhere if less than full flow was required. Talk about wasted energy. This would be equivalent to driving to class with a gas pedal on the floor at all times and modulating your speed around every turn, stoplight, or school zone with regular and constant applications of the brake. In both scenarios, an ample amount of energy is constantly being converted, only to be wasted when less input is required. A far better scenario for those applications necessitating a range of speed values is to think from the bottom up. Long story short, rather than constantly hammering on the gas and intermittently applying the brakes, let off the gas when you want to slow down and step on it when you want to speed up. What is required for applications necessitating variable speed is quite obviously a variable speed motor. Various methods of speed control exist. Some of the earliest variable speed motors were DC motors and are still in use today because DC motors have a linear speed to applied voltage relationship and can develop large torque even at extremely low speeds. We'll examine various configurations of DC motors in later lectures. Another type of variable speed motor is a wound rotor induction motor where rotor resistance is varied, thus affecting the induction process and the resultant speed of the rotor. While effective, this method is notoriously inefficient and does not develop large torque at low speeds like a DC motor. All these methods, while effective, are being largely supplanted by the advent of inexpensive and extremely versatile motor drives. Motor drives are known by many names. Pretty much pick one of these words, variable or adjustable, one of these words, frequency or speed, and one of these words, drive or converter, and then string them together in any order you want, and you've got something I'm calling a motor drive. Acceptable combinations include variable frequency drive, adjustable speed drive, or their numerous interchangeable abbreviations, VFDs, AFDs, VSDs, or ASDs. Regardless of the terminology employed, all of these devices are solid-state power electronics devices that, as some of the titles imply, vary or adjust the magnitude and frequency of applied voltage to a motor under its direction. The same motor will experience a proportionally increased synchronous speed of 3000 RPM. Assuming a 100 Hz maximum output, this motor is now theoretically operable inside a 0 to 3000 RPM range with no quantum jumps between fixed speed levels. But wait, that's not all. In addition to this wondrous quality of finely variable speed control, motor drives offer numerous other features as well, including, but not limited to, soft starts, soft stops, customizable acceleration and deceleration profiles, accessory digital and analog inputs and outputs, allowing remote operation and communication, braking, advanced protection mechanisms, fault display and recording, and the capability of sophisticated closed-loop control. In fact, a full list of motor drive capabilities would not only be tedious, but pointless, since numerous manufacturers offer numerous different models, all with their own hopelessly confusing and non-transferable methods of navigating this thick forest of options. This being said, we'll briefly discuss some general motor drive features and specifications. Before expounding upon the virtues of motor drives, it's worth investigating the magic that occurs inside the magic box known as a motor drive, at least on a general level. Later lectures in power electronics will examine this process in nauseating detail. For our purposes, we can satisfy ourselves with a general overview. If we were to picture the motor drive as a magic box, three-phase AC with fixed magnitude and frequency comes in, and three-phase AC with a different magnitude and frequency comes out, based on the motor drive settings established by the user. At this level of sophistication, a motor drive is therefore a power electronics device known as an AC to AC converter. Internal to this magic box, this process can be visualized as two other power electronics devices. One, a rectifier that converts incoming three-phase AC with fixed magnitude and frequency into DC, another, an inverter that converts DC into an outgoing three-phase AC with adjustable magnitude and frequency. When viewed at this increased level of detail, a motor drive is a rectifier, an AC to DC converter, followed by an inverter, a DC to AC converter. For this reason, motor drives are somewhat mistakenly referred to as inverters, which actually only describes one half of their purpose. The DC voltage in between the two related power electronic stages is sometimes known as the DC bus or the DC link. The DC bus can store tremendously large values of DC voltage and must be treated with caution. For example, a motor drive operated on 120 volt line to neutral and 208 volt line to line light industrial three-phase AC might have an average DC bus value of over 280 volts. Additionally, energy storage devices like capacitors inside the motor drive can store a lethal charge even after being powered off. For this reason, most motor drives include safety and protection mechanisms that are designed to automatically dump the DC bus within a specified amount of time after being powered off. Take the necessary precautions and follow all manufacturers' recommended lockout and tagout procedures. Test and verify the DC bus in the motor drive is discharged prior to working on or around it. Delving deeper into the inner workings of a motor drive, without bottoming out in an unnecessarily technical discussion, we find several additional functional elements. Both the rectifier and inverter portions include filtration circuits to clean up their respective outputs. The rectifier, as previously discussed, is an AC to DC converter that changes the incoming three-phase AC with a fixed magnitude and frequency into DC. Ordinarily, the rectifier is a type of three-phase AC bridge rectifier that produces an output with an inherent ripple. This ripple is removed with a filtration circuit that produces a relatively stable DC value. As mentioned previously, the part of the filtration circuit may include energy storage devices like capacitors that can store a lethal charge if not properly dissipated. We'll examine diodes, thyristors, natural commutation, and three-phase bridge rectifiers that make rectification possible in later lectures. The other half of the motor drive, the inverter, can also be modeled as having two distinct stages. One being the inverter itself, being the part that changes the incoming DC into three-phase AC with a variable magnitude and frequency, the other being filtration circuit that cleans up this stage's respective output. The inverter, in summary, can be viewed as a collection of high-speed solid-state switches that selectively connect or disconnect the DC link for various amounts of time and with a given polarity. The result being a type of pulsed output. When the filtration circuit smooths out the pulsed output, we are left with something mimicking three-phase AC, only this time frequency and magnitude are variable. This type of inversion process is known as pulse width modulation, sometimes commonly referred to using its abbreviation, PWM. Pulse width modulated inversion takes some explanation to understand the process in its entirety. I originally intended to summarize this process in this lecture. However, even the summary is a little lengthy. Let's hold this topic off for another lecture. For now, put your hand on top of the internet and repeat after me. I, state your name, believe. I believe a motor drive accepts incoming three-phase AC with a fixed magnitude and frequency, rectifies it all to DC, then outputs three-phase AC with a variable magnitude and frequency. Like I said, we'll explore this faith-based mystery in a later lecture. However, realize this rectification and subsequent inversion process is not without its limits, because very often the output of a motor drive is electrically noisy, sometimes characterized by high voltage spikes at the output, even after filtration.